Our lesson 1-1. So last class we learned a certain particular technique to factor what we call trinomials. What was our technique? X method. Yes. This bell ringer really what it does is it addresses X method factoring and specifically how we might use it in pre-calculus. So I'm going to focus with number 1 here. So the bell ringer is always going to be kind of just a review of what we learned the previous day, and I like to give it to you as a test form of a question so that there's no surprises whenever the test time comes around. You kind of know what to expect. So number 1 says, write a function g of x that results by simplifying the rational function f of x. And really what we're going to need to do is we're going to need to x factor both the numerator and the denominator and then simplify to get our solution here. So I'm going to start with the numerator. If you wouldn't mind, Bianca. Okay. Anybody else? I'm going to start here by x factoring the numerator. Do y'all remember what was step 1 last class when we were learning how to x factor? It's to look for the greatest common factor, GCF. Okay, so as we look at the numerator, between the 3 terms, 2x squared plus x minus 15, is there anything in common across those 3? I'll see anything in common? No, so there's no GCF. And so step 2 last class, we then moved into the x method. If you remember, you take the a times the c value and put that at the top of the x, and we're going to place our b value down below. So in this problem, a is 2, b is the number that would be in front of the x that we don't see right now. C is negative 15. What is b if you don't see a number, but you do see an x? 1. That's right. So 1 is the b value. So when I fill this in, we have 2 times negative 15, which is 2 times negative 15, negative 30. And then down in the denominator, I'm looking in the wrong spot. I'm sorry. B is 1. There we go. Sorry about that. Lost what I was doing there for a second. And now we try to come up with 2 numbers that would multiply to be negative 30, but add to be that b value of 1. And so last class I was saying a very helpful tool is a little t-chart. If you have a t-chart, what you can do is list out the factors of 30 and see which one of them happens to be, can combine to be a 1 somehow. So the factors of 30 are 1 and 30, 2 times 15, and you're right, we could have positives or negatives. I'll get to that in a second. I'm gonna just complete the list first, and then we'll talk negatives and positives. So I have 1 and 30, 2 times 15. What about 3? 3 times what is 30? 10. Again, I'll get to the negative in a second. 3 times 10, let's see, 4 does not go into 30, 5 does. How many times does 5 go into 30? 6. And the next number would be 6, but that would be 6 and 5. And we already have that in the list, so I don't need to keep on going. I can stop there. So now I know it needs to multiply to be negative 30, which means there has to be a negative in here. So somehow there's going to be a negative. I want to know which one could somehow give me a 1. 1 and 30, 2 and 15, 3 and 10, or 5 and 6. I'm hearing 5 and 6. I agree. I can get to a 1 value, adding and subtracting using the numbers 5 and 6. Would it be 5 minus 6, 6 minus 5, negative 5, negative 6? What gives me a combination of 1? How about 6 minus 5? I like that. 6 minus 5 is 1. 6 minus 5. So those are our numbers there. So after we've completed the x, we go on to step 3, which you might remember is you split the a terms power. Now last class I just wrote split a power for short. But since we're only doing this a couple times, I'm going to write it out fully. Split the a terms power. So really what I'm looking at is this 2x squared right there. I'm going to take 2x squared and I'm going to split its power. So no longer will it be 2x squared. When I split a square in half, it becomes an x. So it's just 2x and another 2x. So my a terms power was squared, so I split it. So now I have 2x and 2x, and then I put these two side numbers, plus 6 and minus 5. The last step, we had 4 steps, was bottoms up. And that's where you look and see if either factor can be simplified. Could I simplify the first factor? Yeah, I hear 2 goes into the first factor. Do y'all agree with Ellen? Yeah, 2 can go into that. What about the back factor? Anything shared there? No, that one's going to remain the same. So that means the numerator could be simplified as x plus 3 times 2x minus 5. What I'm going to do with that is up here where it says f of x equals, I'm just going to rewrite it and put the numerator up there so we have it. The numerator factors is x plus 3 times 2x minus 5. Okay, that might seem like a lot of work, but guess what? We're only halfway done. We're going to do this all over again for the denominator. I'll do a little divider. I won't write out the steps this time, but I will write out the denominator on the other side. Let's check out the denominator. The denominator, if I look for GCF, is there any GCF between 2x squared negative 19x and positive 35? No. So we move on. Very good. So we're going to do X method now. Whoops. X method. So I have A times C. B in the bottom. For our denominator, we have 2 times 35. Anybody know mental math? 2 times 35? 70. Good. And B is negative 19. So now we're going to look for the two numbers. I'll call them M and N. That multiply to be 70, but add to be negative 19. So starting my list, I have 1 and 70. We, of course, have 2 and 35. Okay, 3. Does 3 go into 70? 3 goes into 60, then 9 go into 70. Okay, what about 4? 4 would go into 80, so no, it won't go into 70. What about 5? 5 does 14 times, and 7 also does. 6 does not, but 7 does. 7 goes in how many times? 10. Okay, out of this list, we got to get a combo of negative 19. Which one could somehow be a 19? 5 and 14. Okay, if they were both positive, it's positive 19. So how do I make it a negative 19? Both negatives. Very good. So it needs to be a negative 5 times a negative 14 to get a positive 70. A negative 5 minus 14 more to be a negative 19. All right. Step 3 said split the A terms power. So I'm now splitting a 2x squared again. So we'll have a 2x and a 2x. I'm splitting this A terms power. Our side numbers are minus 5 and minus 14. Last step, bottoms up. Anything common in the first factor? What about the second factor? 2 goes into both, which leaves us with 2x minus 5 times x minus 7. Put that up here. And we are ready to get our answer now. So the problem, the instruction said, write a function g of x that results by simplifying this rational function. What you're not allowed to do in mathematics is cancel what we call terms. You're not allowed to cancel terms. Not allowed to do what I just did there. Can't cancel a term, but you can cancel factors. It is mathematically accurate to cancel factors. So here I could cancel the 2x minus 5s, and now we know our solution. G of x is the simplified form, which would be in the numerator x plus 3. Now that I only have one factor, you don't need the parentheses, over x minus 7. That's my solution right there. Before we move on, do you want to, I can give you like 10 minutes. Would you like to try number 2 as tables and me walk the room and then go over at the end, or you want me to walk through it from start to finish? All right, 10 minutes. Y'all try it on your own. All right, so on the numerator, was there a GCF? No, so I can skip step 1. On step 2, it's X method. Step 2 is X method. So we're looking for factors of A times C, which happen to be -12, that add up to be our B value of -1. All right, what two numbers did y'all come up with for this? Speak once and you're out. That means this whole classroom, you can't answer another one on the bell ringer. So it's going to take the whole classroom basically to solve the problem. So speak once and you're out. -4, +3 is the correct numbers. Great. Okay, from there, Ellen, you're out. Can't answer again on the bell ringer. What happens next? Somebody else. What's step 3? All right, Kyra, split the A term. So 6x squared gets split and it becomes 6x and 6x. Kyra, you're out. Let me fill in the -4 and the +3. Someone else. Bottoms up, what does that mean? Divide by what? 2 and so is that Diana and Alexis, I think? Is it not Diana? Is it Jacqueline? Jalissa? Okay, Jalissa's out. She's trying to give credit away. I'm going to call her out. All right, so what do we simplify to? 3x minus 2 and? All right, so now let's do this all over. That's the numerator. Let's do this all over again. This time, let's focus on the denominator. A, B, C. Is there a GCF here?
No.
No. You spoke, you're no, just kidding. 3 times -14. -42. Louisa, you're out. And then B is 19. I didn't hear who that was. But you know you're out. All right. 2 factors. So there could be 1 and 42, 2 and 21, 3 and -2 and +21. Let me write it the other way so we can see it. 21 minus 2. I agree. That is 19. Is 21 times -2 -42? I think so. Whoever said that is out. So next step. Split A. So this time I'm splitting 3x squared. So is this one, Diana?
No.
So I have 3x plus 21 and 3x minus 2. Bottoms up here. What divides into the front end? 3. So we have x plus 7 and 3x minus 2. Okay, so what that means is f of x equation, as I gave it to you, was standard form up the top, or originally was standard form. In factored form, it would look like this. The numerator 3x minus 2 times 2x plus 1, and the denominator x plus 7 times 3x minus 2. Now that's the equation f of x. Oh wait, I think on yours, I don't actually call it f of x. Do I call it a and b? Yeah, let me do it the way your packet says. I think I have a and b. So b of x would then be the simplified form. How could I simplify a of x here? I could cancel those out. And so we are left with 2x plus 1 over x plus 7. That would be our solution there. We're going to look at functions today. So if we open up our packets, I want to go to example 1. What we're first going to talk about are different kind of numbers and how we write out values. I'm going to actually go through example 1 really quickly because I don't focus much time on this in pre-calculus, but I do want you to know this. in a lot of classes, you've given the symbol for all reals as a double R. Why does it keep showing me a line? I don't want to see a dotted line. There you go. Have you seen that double R thing mean all reals? That means just anything that's a real number. What's something you don't see as often is a double N. And a double N just means it's the natural numbers like counting numbers. So on part A, example 1A, when it says 2, 3, 4, 5, 6, those are counting numbers. That's not all reals. For example, is there a number that you could find if we're talking money that's in between $2 and $3? Is there something in between $2 and $3? Yeah, someone could have 250, right? So this wouldn't be all reals, but what you could say is that this is the numbers from 2 is less than or equal to x, which is less than or equal to 7, if x is a counting number only. And so the way you would write that is x e double n. That means it's only the counting numbers, no decimals. Okay, that's one way of writing it. It says using set builder. I use, that was what I just wrote is called inequality. Whoops, inequality. This means I'm not using an equal sign. Or I should say inequalities. Since I have multiple. I'm not using just a straight up equal sign. I'm using less thans and greater than symbols. Okay, so that's part A. Now on part B, they give me an inequality, and this time I'm going to write it in what we call interval notation. So I'm going to scratch that out and put interval. And the reason I'm doing this is because I'm using what you will see most often in my class. I want you to be familiar with these. So on this problem, it's saying x can be anything larger than 17. In interval notation, I think I said 17, I meant negative 17. In interval notation, here's how you would write that. You would say parentheses, negative 17, comma, infinity. What this means is the parenthesis said it's going to be not equal to. So just like this does not have a line underneath it, it's not equal to, it's just greater than. And then we are bigger than negative 17. So when you write interval notation, you put the smallest on the left, largest on the right. Since there is no largest number, I'll just put infinity because that just means it goes on forever. It's like Buzz Lightyear. It just goes on to infinity and then beyond. And finally, part C, describing all multiples of 7. I don't want to spend too much time here, and so I'm not. But what I will show you is if you were to write those out, multiples of 7, so you would have like 7, 14, 21, 28, etc. Now, I'm not going to spend any more time on that. We're not going to use that this year. So I don't even want to, I have other things I'd rather spend time on. So with that, what I do want you to draw your attention to, the name of this is called inequalities because they use symbols that are not equal signs. This is called interval notation. They use either brackets or parentheses. So far, you've only seen parentheses. All right, your first DOL for today. And from here on out, the rest of the year, the DOLs are going to be what you see as a guided practice. That means it's a DOL. It says describe the number 6, 7, 8, 9, 10. And I'm not going to tell you what ... means. I'm going to see if you know. But I want you to use, this is what set builder is. I want you to determine the correct answer. So I'll give you a few seconds. I'll give you about 30 seconds to try to come up with what you believe the answer is. All right, now let's practice a little bit more of converting between interval and inequality in the notation, okay? David, make sure you're with me, please. Keep that up, I appreciate it. All right, so we're looking at -2 is less than or equal to x, which is less than or equal to 12. And it says use interval notation. This is the type you'll see me use throughout the year, both inequalities, that's here, and what I'm about to write, interval. So interval, anytime you have an equal to, like less than or equal to, you use a bracket. Why does it keep going back to that? You use a bracket. So I'm going to say bracket, -2 is the smaller number, 12 is the larger number. Because I can be equal to 12 as well, I use a bracket. So you might remember on the previous slide, I used a parenthesis. That's if you're not equal to, if it's just greater than or less than. But if you can be equal to, you use brackets. So that's interval notation there that I have circled. All right, next one. We have x is greater than -4. So will that be a bracket or parenthesis? Parentheses. So it's a parenthesis. And now the question, if x is greater than -4, does that mean -4 is the smallest or the largest? Smallest. So that means -4 goes first. And with inequalities, if you don't have a second symbol, you replace it with infinity. So it'll be -4 to infinity. Okay. So can we be equal to -4? No. So parenthesis. Infinity, you can never equal either. It's always a parenthesis as well. And if you're going, why is that? Well, if we took all 8 billion people that are on the planet Earth and we stuffed them in our classroom and we all put out our fingers and we try to count the total number of fingers, would we get the number infinity? No, we'd have 8 billion times 10 on average. Not that everybody would have 10 fingers, but most people would. You just have 8 billion times 10, you'd have 80 billion fingers. You wouldn't ever get to infinity because that it's not a real number. So that's why it's always a parenthesis. It's more of an idea. Okay, and finally, C, when you have this word or, what that means is you have a union. You have more than one piece. If you're looking at a graph, it would look like it would resemble more than one piece of graph. So we have x is less than 3 or x is greater than 54. I'm going to start with the smallest number. X is less than 3. Does that mean 3 is on the high end or the small end of this interval? High. X is less than 3. So 3 is on the larger end. Bracket or parenthesis on the 3? Parenthesis. So what goes on the left end? I hear infinity, but if it's on the left end, it'll be a negative infinity. So you have a negative infinity, comma 3, close it with parentheses, union, that means or. Over here it says x is greater than or equal to 54. So is 54, can x be bigger than 54 or less than 54?
Yes.
This is saying x is greater than or equal to 54, which means 54 is on the small end on this side. Can I bracket or parenthesis? Right. It has the equal to sign, so bracket. Hey, David, come on now. And so what do I replace with the unknown, or if I only have one value? Infinity, parenthesis. That would be our solution this time. All right, DOL number 2. I'll give you about a minute to come up with your solution here. Now let's talk about a function. If you remember from your algebra, a function is defined as any type of relation where the domain, each and every element of the domain is unique and only used one time. So each member of the domain has one and exactly one member of the range. Now the range can be used multiple times. So here in this set, when you're looking at drawing a set from A to B here, even though in the range, the B, 7 is not used and 8 is used twice, that's fine. All you're looking at is the domain. Each element of the domain is used one time and only one time. It has a unique one value that it goes to. What would not be a function is if the domain had two values. This would no longer be a function if, if this had an arrow there. That's no longer a function because 2 is used twice. It's no longer a function. So each element of the domain is only used one time. Graphically, you could use a vertical line test to determine if it's a function or not. So now I'm going to give you a few examples, and we're going to determine if these are functions or not functions. These are real world. So that's what pre-calculus really is. It's all the math knowledge you know put to real world. So here's the first example. It says the input value, X, is the height of a student in inches, and the output, Y, is the number of books the students own. So I want you to consider let's say here's the students in our classroom, and we were going to write down all your heights. And there's the student. Whoops, I don't know why I wrote students. I'm sorry. We want to write height. The height is our domain. The number of books you own is the range. If we got all your heights, I listed it out. Let's say the shortest person in here. I'm just going to go roughly feet. So let's say 4 feet, 5 feet, 6 feet, and everything in between. So maybe the tallest in here, I don't know, is 6 feet, 4 inches. And if I had everyone listed and you drew arrows to the books, what do you think? Would it be a function or not a function?
Function.
So that would mean that every value, if you're say 5 feet tall, everyone who's 5 feet tall would own the exact same number of books. Do you think that would be right? No. Some people who are 5 feet tall might own 10 books. Someone else who's 5 feet tall might own 1,000 books. Does your height have anything to do with how many books you own?
No.
No. For that reason, this is not a function. It's not a function, and if it's not a function, what we'll call it is a relation. So it's not a function. We would call this a relation. A relation does not mean, is not the opposite of a function. A relation just means the two things are connected, but they're not connected as a function. That's all it means. There is a relationship. That's where we get relation from. There is a relationship, but it's not a functional relationship. All right, what about part B here? This time I'm giving you a different representation, a table. What do you think? 5, 4, 3, 2, and 1. Would that be a function or not a function?
No.
Oh, not a function. What blows it up? 2 4s do. They have different y's, as well as the 1s. You have 1s with different values of y's. This is not a function. So again, there's a relationship, but it's not a functional relationship. So what do we call it? Just a relation. Good. Okay. Now let's go to a graph. Here's a parabola. Let me get a vertical line. Remember your vertical line test. All right, you're looking to see, does this parabola pass the vertical line test? What do you think? 3, 2, 1. Function, not a function.
Function.
Good, it's a function. Remember, the vertical line test just means it can only touch the graph one place at any one time. So it can't ever cross twice. So if you want to say, what would it look like if it was not a function? Something like this. Now, you see how my vertical line's hitting the graph twice? That would mean this would not be a function if it was turned sideways like that. But as it was given, it is a function. So this is a function. And one more. Determine whether x equals 3y squared represents y as a function of x. Okay, we need to graph this. I'm going to use Desmos. I like Desmos. Desmos.com/calculator if you want to go to that, or you can just watch me type it in. X equals 3y squared. X equals 3y squared. Here's the graph. What do you think? Not a function. This fails the vertical line test. So this would not be a function. So what would we call it instead? A relation. That's right. And so now we have our answers, and you're ready for your next DOL. So let me write this on there. Not a function. I think you're ready for DOL number 3. Again, if you want to know what are going to be my DOLs, it's the ones that say guided practice. So on the next slide, determine whether this equation 12x squared plus 4y equals 8 represents y as a function of x. I'll give you a little while to graph it and check out on your own. All right, moving on with functions. So with functions, they can do something very powerful. One of the things you can do with functions is find function value. So here it says f of x, the function f, that's what that those symbols mean there. The function f equals x squared minus 2x minus 8. Well, what can we use that for in the real world? Well, it represents that this function can supply all kinds of different values. And in particular, we want to look at if the domain, that's the input, the x represents domain. If I replace the domain with a value of 3, what will be my range for the domain value of 3? What will be my output if my input is 3? So I'll walk you through the math here. What you do is anywhere you see an x, you replace that with a 3 as I have done, and then you just simplify. 3 squared, what is 3 times 3? 9. And then we have minus 2 times 3. Well, what is 2 times 3? So we're going to subtract 6, and then we'll subtract 8. So when I subtract across, 9 minus 6 is 3, and then I subtract 8 more. 3 minus 8 is -5. And that would be my solution. F of 3 would equal -5. Now, there's more than one way of doing this. I went through the math. That is so ugly. Let me try writing this again. Okay, what we could have done is come over to Desmos, and I could have typed this in. I want you to see this. So, hey, stay with me, please. This is helpful for a lot of students knowing how to do this. If you type this into Desmos and include the f of x, what you've actually done is program Desmos to know the function f. Now it knows the function f. I could just say f of 3, and it would give me the answer. Notice it says -5 right there, because it knows what the function is. Another way of doing this is if you go to table, it would show you at 3 that the value is -5, which refers to this point over here. When x is 3, it's this point right there, 3, -5. Notice, whoa, what did I write over there? No one corrected me. Y'all were all wondering, do we correct him? Yes, you correct me when I'm an idiot. -5 is the answer there. All right, let's try part B here. Part B says if f of x equals, well, same equation, find f of -3d. So same concept, but this time we're going to look at, you don't have to be substituting in an integer. You could really substitute anything in to the function f. So what I'm going to do, again, is anywhere I see an x, the x is going to get replaced, this time with -3d. I use a parentheses because it just helps make sure I keep my math in order and I do things correctly. All right, -3d squared. That means -3d times -3d. Two negatives make a positive, so it'll be positive. What's 3 times 3? 9. There you go. 9, and d times d would be d squared. So we have positive 9d squared. Now I have a -2 times a -3d. What's a -2 times a -3? Two negatives make a positive. 2 times 3 is 6, and then the d, okay, -8. This value cannot be simplified any further. So that would be my solution there. You could try to see if you could factor it, but I'm not worried about that. It is a trinomial, so you could try X method, but I'm not worried about that in this problem. And now part C says if f of x, again, same equation, but this time it says find f of 2a minus 1. So I will substitute in 2a minus 1 this time. So technically what I'm doing on all three of these parts is what I'm exchanging the domain, which means I'm changing what is going into the function. And because I change the domain each time and it's a function, I'm getting a new range value each time. There's your terminology. So once again, I'm substituting in 2a minus 1 inside the parentheses all the way across. What's going to be a little trickier is this portion. In math, one thing you cannot do is distribute a square backwards through a parenthesis like that. That would be terrible math. You can't just square each term. Does not work that way. So the way to solve this, when you have a group squared, so the previous one, it was not a group. Now I have a group 2a minus 1. You need to write out the parentheses twice and distribute from there. Some teachers call this foiling. You might remember FOIL, which stands for multiply first times the first, outside times the outside, inside times the inside, and then last times the last. That's what I'm going to do here. First times first. What is 2a times 2a? 4a squared. What is 2a times a negative 1? 2a times a negative 1. This is the O. Outside times outside is a negative 2. Negative 2a, I guess I should say. Okay, what about the inside times inside? Negative 1 times 2a. Another negative 2a. And then negative 1 times negative 1. Positive 1. Okay, so that's this portion. Now let's look at negative 2 times 2a minus 1. I need to distribute this as well. What's negative 2 times 2a? Negative 4a. Negative 4 with the a. Okay, and then what's negative 2 times a negative 1? Positive 2. Good. And then finally, the minus 8. Once we simplify this, we'll have our solution. F of 2a minus 1 will equal, I'm looking, I only see 4a squared once. Got it. I see I have a couple different a terms here. I have a negative 2a, another negative 2a, and a negative 4a. I like thinking in terms of money. With negatives, that means you owe someone money. And instead of saying a, I'm going to say dollars. I owe someone $2. I owe another person $2. I owe a third person $4. I'm what you call broke. Okay, what's I owe 2? I owe another person 2. I owe another person 4. How much do I owe? $8. So I owe $8. And then finally, we have positive 1 plus 2. That's 3. And then I subtract 8. What's 3 minus 8? Minus 5. That would be my equation there. Unfortunately, I do not think Desmos would solve this for us. Yeah, it won't do it with a variable in there. It will do it if it's an integer. All right, so with all that, I'm going to give you a DOL, and I'm going to give you a couple minutes to work on it. I want you to try to find this value here. Given this function, find f of 6. Now, I'm going to give you a very helpful tool because a lot of students in the previous school years, I know, break down when they get here and they're like, well, we didn't work one like this. Here's what I recommend. First, find f of 6 in the numerator, and then eliminate any answer that does not give you that numerator. Then find f of 6 in the denominator. Eliminate by denominators, and you ought to be able to come up with the only answer up there. So plug in 6 to your numerator, plug in 6 to your denominator. All right, now domain. This is one of my favorite parts to teach because I've realized over the years that a lot of teachers don't teach it this way, and domain for many students is difficult. But I feel like in my class, a lot of students start to get it. They're like, oh, I didn't realize it was so simple when you break it down into concepts. Here's the deal for domain. Domain is all reals. You assume a domain to always exist unless something breaks it apart, like it breaks some type of math rule. So if you know your rules, domain's real easy. So you always assume it's all reals. You assume a function's domain is all reals unless it breaks a rule. So what are the rules? Right now, you know 2 rules before you enter my class. We will learn a 3rd rule in October or so. So here they are. Write this on your paper. There are 2 rules you know. One has to do with division. You learned you cannot divide by a certain number. What number can you not divide by?
0.
Very good. You cannot divide by 0. That's the first rule you've learned. A second rule has to deal with square roots. You cannot take what type of square root are you not allowed to have? You are allowed to take the square root of 0. The square root of 0 is 0. So it's not that. The square root of 1 is 1. A negative, very good. You cannot take a negative square root. Now, there will be a 3rd rule that will come later. So you can just put to be determined, TBD. You'll learn what that one is later on. But for today, I'm going to focus on these 2 rules. There are symbols to help you with this domain. Here are the symbols. The symbols for cannot divide by 0, I do it this way. 1 over x cannot equal 0. That means when you divide, that's what that slash means. Whatever's in the denominator, x just means whatever. Whatever's in the denominator cannot equal 0. That's your symbol. For square roots, the way to say something cannot be negative is to say it either has to be 0 or positive. So whatever's inside the square root, that's what x represents. Whatever's down there has to be greater than or equal to 0. That's the idea, or that's how you find domain given any function. So you assume it's all reals unless it breaks a rule. So now that we know our rules, let's go solve the domain of G here. When you look at G, which rule might it break? Rule 1, rule 2, or none? Rule number 2. What did you see that makes you think rule number 2? What symbol? Okay, not the -1. Something else should be triggering for rule 2. What symbol is that called? A square root. When you see a square root, what I hope goes in your mind is that square root cannot be negative. That's the rule. It cannot be negative. So how do you solve it? You take whatever's on the inside of the square root, which in this case is 4x minus 1. You take whatever's inside the square root, and you say that value has to be greater than or equal to 0. That's our symbol. So step 1 is just figuring out what portion of the function to take and how do I set it compared to 0. In this case, it's got to be greater than or equal to 0. From there, it's algebra 1. You just solve this algebra 1 style to get our answer. If I'm solving for x, you do the opposite of the operations you see. For example, this says 4x minus 1. What's the opposite of minusing 1? Plus 1. So I'm trying to find the domain, which means the values that x could potentially be. So I add 1. So now I have that 4x is greater than or equal to 1. I have one step. 4x. Does that mean 4 plus x, 4 minus x, 4 times x, 4 cubed x? What does that mean when you have a 4 next to an x? Times. What's the opposite operation of a multiplication? Division. So if we divide by 4, we should have our solution. This says the domain, which means the x values, is that x has to be greater than or equal to 1/4. Like I said before, you assume at the start that x is all reals. That's how we assume. We think it's going to be all reals. But then if you see a rule breaker, you limit it. And so in this particular case, x has to be greater than 1/4. Let's look at a picture of the graph and see if this is right. So I'm going to go take this equation, g of x, and graph it. G of x equals the square root 4x minus 1. Now I want you to look at this picture. Remember, domain means left and right, x values. Does the domain go forever to the left? Do you see the graph on the left side of the y-axis? Yes or no? Is the graph going forever to the left? No. It is going forever, though, towards the right. And so now the question is, where does this graph begin at? If I zoomed in right here on Desmos, it's going to give it as a decimal. It says 0.25. What is 0.25 as a decimal, as a fraction? 1/4. So we did do it correctly. What this was saying here, and I'll write it now in interval notation, that's inequalities. Interval notation, it's saying the graph began at 1/4. I used a bracket because it was an equal to. It began on 1/4 and it goes to infinity the other way. I know it goes on to infinity because there was no other symbol there. So now let's look at the picture. I'll zoom way out and you will see it goes on forever and ever and ever. The more I zoom out, it just keeps going to the right. That domain continues on. Okay, so that was number one. I want to show you a couple more things. That was only 3 steps, by the way. I feel like, wait, it was only 3 steps? Yes. Step 1 was to figure out what type of symbol to compare that inside of the square root with 0. And the answer was a greater than or equal. That was step 1. Step 2 was to add 1 both sides. Step 3 was divide by 4. And we had our answer. 3 steps. Let's do it again. Same 3 steps. I'm gonna, on the left side, write out the rules. I won't write out the English version of the rules, but I will do this. Rule 1 is you cannot divide by 0. So I'll do x cannot equal 0 in the denominator. That represents rule 1. So you can see what I'm doing. That's rule 1. Rule 2 was that if you have a square root, it's got to be greater than or equal to 0. Okay, let's look at our problem. On this problem, what do you assume the domain of h of t is going to be at the start? Said it twice. You always assume at the start the domain is all reals. What changes that is if it breaks a rule. Will this potentially break a rule? Do you see division? Do you see a square root? Division. So we might break rule 1. So here's what you do. You take the portion that might be a rule breaker. Will 3t squared potentially be dividing by 0? I'm trying to set this in your mind. Listen carefully. Is 3t squared doing any dividing? Someone take a guess. It's a yes or no question. Is 3t squared doing the dividing?
No.
No. This will not change the domain. What will change the domain is the division portion. So I'm not going to pay attention to the 3t squared. I'm going to pay attention to the division. My rule says the denominator cannot equal 0. So you take the denominator and you say that t squared minus 1 cannot equal 0. That's my symbol. Now make sure you're not lost. What I'm doing is I'm looking at the equation and I notice, oh, there's a division. So I took what's in the denominator and I put it next to a cannot equal 0. That's step 1. We have 2 steps left. I'm trying to solve for t squared. How do you get rid of a minus 1?
Make it a
Plus 1. So I'm doing the opposite operation than what you see. So I will have t squared cannot equal positive 1. Now I need to get rid of a square. What's the opposite operation of a square? Square root. Now there's a rule in mathematics. When you add a square root that's not originally there, it needs to come with a plus or minus. You're going to hear me say that all throughout the year. You only have to put it on the side that does not cancel. On this side, it's going to cancel, so it doesn't matter. But on this side, you need to have it. And so what we're left with is that t cannot equal, cannot equal plus or minus, what is the square root of 1? 1. Other than that, t can be all real numbers. It's just t cannot equal positive 1 or negative 1. Any other number it could equal. So let's look at the picture and see if this is accurate. We're saying the graph will equal every single place other than positive 1 and negative 1. So h of t equals 3t squared over t squared minus 1. Did I get that right? Yes. Looking at this picture, overall, does the graph exist most places? Does it go left forever? Does it go left forever? Does it go right forever? Yes, it does. I see 2 breaks. You might be thinking, how do you see 2 breaks? Well, I have 3 pieces. If I had a pencil, well, I do have one. There's 3 pieces. If there's 3 pieces and you try to connect them together, but there's 3 pieces, that means it's been broken how many times? You say 3, that's not right. If it was 1 piece, how many breaks would it have? Look at my arm. If there was 1 piece, how many breaks would there be?
2.
My arm has 2 breaks.
One.
Whoa, look at my arm. You see a break there?
No.
No breaks. 1 arm would be
One more.
1 break or no breaks.
Wait.
I don't want to confuse you. It's not a trick. 1 arm.
One more.
Is my arm broken? No breaks. Okay, if there's 2 on a graph, how many breaks are there? There's now 1 break between the 2. You see that 1 gap? Okay, so if there's 3 pieces, how many breaks are there? 2. Okay, this graph has 2 breaks. Any guesses where those 2 breaks are going to be?
Right there in the middle.
They're going to be at positive 1 and negative 1. Let's check it out. I'm going to do table at positive 1 and negative 1. What does it say? Undefined. And look, I could add a whole lot more numbers. The only 2 breaks are at negative 1 and positive 1. That's where this graph is broken apart. At negative 1 and positive 1, this graph breaks apart, and that's where the breaks are. We did the math correctly. Now, what I'm trying to say is, you might not right now be going, okay, I got to work on this algebra. I don't understand what he's saying. But I think it's easier than looking at this graph, than looking at the graph and going, oh, my domain is all reals except for negative 1 and 1. I feel like it's a little bit harder. It's a lot easier just to learn your rules and solve it in 3 steps. By the way, this is called an inequality. If you wanted to write it as an interval notation, you would say the graph can go left forever, so negative infinity. Where was the first break locating at? From left to right. What number broke apart these 2 pieces? Negative 1, good. At negative 1, you have a break. How you symbolize that is you do parentheses, union. That means break. And then you pick back up on negative 1 on this side, and you go to positive 1. And then it breaks, and this piece picks up at positive 1 again and goes to infinity. That's the other way of writing out this domain. All right, I'm going to do another. Part C here. I have a crazy equation again. Domain rules, there are 2 of them. What's rule number 1? Okay, someone other than Ellen. What's domain rule number 1? You cannot divide by 0. So I'll do x cannot equal 0 in the denominator. What's rule number 2? No negative square roots, which means x has to be greater than or equal to 0. All right, let's look at our problem here. Do you see a division? If you see a division, what does that mean about the denominator? What can you tell me about this denominator? Come on now, hey, pay attention here. You can take guesses. It's not, you're no fault if you're wrong. But if you just kind of quit answering, you fall asleep, and that's no good. I'm gonna ask it again. Do you see a denominator? Yes. What has to be true of the denominator? It cannot equal 0. Thank you. The denominator cannot equal 0. That means 2x minus 3. The square root of 2x minus 3 cannot equal 0. Second question. Do you see a square root?
Yeah.
Yes.
Yeah.
What can you tell me about the inside of the square root? It has to be greater than or equal 0. So both rules are true. So this is saying I cannot equal. This saying I have to be greater than or equal. Guess what? Since I cannot equal, I'm going to eliminate that. And this time, I'm going to take this denominator, 2x minus 3, and I'm going to say that has to be greater than 0. Now, some of you are like, wait, why does it have to be greater than 0? Let me show you by number line. With the two rules. Rule number 1, you check. Do I have a denominator?
Yes.
Yes. As soon as I say I have a denominator, my value cannot equal 0. That means it could be negative, it could be positive, but it cannot equal 0. Then I asked, did it have a square root? Does this have a square root?
Yes.
What does a square root eliminate? Square roots cannot be negatives. That eliminates all negative numbers. What's left over? The positives. So I'm saying 2x minus 3 has to be greater than 0. That means positive. My answer has to be positive here. So let's now solve this. It's 3 steps. There's step 1. What's step 2? You're solving for x. Add 3. I'm trying to get x isolated. So I need to do the opposite math that I see. I'm subtracting 3. The opposite of subtracting 3 is adding 3. Now we have that 2x has to be greater than 3. All right, that 2 is next to x. Does that mean 2 plus x, 2 minus x, 2 times x, 2 times? What's the opposite of multiplication? Division. You divide by 2, we have our solution. X has to be greater than 3/2. Okay, different question. I forgot to ask at the start. What do we assume the domain to be at the start? All real numbers. What this is saying is it's no longer all real numbers. It's all real numbers that are greater than 3/2 or greater than 1.5. That's what we just determined. This graph will be all values of x. So x is that flat axis. All x values that are greater than 1.5. Let me graph it to you so you can see and realize, wow, the math actually works. It's a beautiful thing once you realize, man, math actually works. It's not just something crazy. It does something. 2x minus 3. Okay, here's this crazy graph. I want you to look at it. This graph does go on forever to the right, but it doesn't go forever left. I'm going to change the color. Let me get a different color. Here we go. All right, looking at this graph, does it go to the negative side? No, we know it doesn't go left of 0. This says it doesn't go left of 1.5. Let's check that out by the table. Does it exist at 1? Does it exist at 1.5? No, we said it has to be bigger than 1.5. What's a really, really small number that's bigger than 1.5? How about 1.51? Does the graph exist there? You bet. 1.6, does it exist there? Yeah, the graph is anything bigger than 1.5. Anything bigger than 1.5, the graph exists. And so we got it correct. And it goes on forever to infinity. Just for good measure, here it is in interval notation. You would say parentheses, 3/2 to infinity. 3/2 is the smallest. It's a parenthesis because it's not equal to. It goes on to infinity. Okay, I want to give you one more before I ask you to do it yourself. So question 1 I have for you. Before you even look at the problem, what are you going to assume the domain is before you even look at it? All real numbers. You always start there. A function you assume is all real numbers. Now we have assumed it. We look at the problem. Do you stick with your assumption or is your assumption changed? Meaning, do we break a rule or do we not break a rule in this problem? I see a square root. Is there a rule with a square root? Okay, let me ask this question. How many rules are there? 2. What are the 2 rules? You cannot divide by 0? Okay. Cannot divide by 0 and no negative square roots, which means x is greater than or equal to 0. Okay. On this problem, do you see either of those 2 symbols, division or square root? Square root. My domain will not stay all reals. Why will it not stay all reals? Because I have a square root. So you take the inside portion of the square root, 25 minus x squared, and I say that has to be greater than or equal to 0. That's step 1, is just getting your rule breaking portion with the correct inequality. Step 2. I need to solve for x squared. I'm going to do this one a little different just because I like positives. I don't like working with negatives as much. I'm going to add x squared to both sides. So now I have 25 is greater than or equal to x squared. We had this rule earlier, or this operation. How do you get rid of a squared? What's the opposite operation? Square root. And I told you something that is a rule of square roots. Anytime you add a square root that's not originally there, what needs to come with it? A plus or minus. You put it on the side that's not going to be reduced or canceled. So I put it on this side. And so now I go to write my answer. Okay, lock in here. This part is, you might say this whole thing's been confusing, or it might have totally understood. Either way, we're gonna have a lot of practice. But here's one thing that a lot of students forget because it's been since like 7th grade, since you dealt with inequalities. When I write this, do y'all know what the square root of 25 is? 5. The first thing I'm gonna write is that the positive. Positive square root of 25 is positive 5 is greater than or equal to x. But when you add in a negative, I don't know if you remember this with inequalities, if you add a negative that wasn't there, you have to change the direction of the inequality. Y'all remember that rule? Okay, so for my second answer, negative 5, I have to say that is less than or equal to x. And so I have both of these. With inequalities, sometimes they can be put together and sometimes they can't. I don't have a good way, a trick of showing you put them together or not, and other than to pick a number. So Elizabeth, this says 5 is greater than or equal to x. Pick a number that is smaller than 5.
3.
She says 3. We have 3 here. 5 is greater than 3. Do y'all agree with that? 5 is greater than 3. Okay, let's see if it also passes this rule. This says that negative 5 is smaller than or equal to x. Is negative 5 smaller than 3? Okay, so we pick 3, and it's true for both. If it's true for both, you can put them together as one inequality. Negative 5 is less than or equal to x, which is less than or equal to positive 5. X is all reals in between those 2 values. That means my graph will exist from negative 5 to 5. Shown by inequalities, this picture will exist between negative 5 and 5. Let's take a peek. F of x was the square root of 25 minus x squared. I want you to look at this picture. Does this graph go forever to the left, forever to the right? No, it has a stopping point. Where's the stopping point at on the left side? What about on the right? positive 5. That's how we got it. Now, let's say we got symbols where the number was not true both times. So Elizabeth said 3. If it would not have been true for both, that's when you say or. This or that. That's when you'd have an or. With all of that, I'm going to give you your DOL. DOL number 5. I want you to solve this one. Use those 2 rules. Get your answer here. All right, last thing here is called piecewise. For functions, this is the last thing that we really need to know for pre-calculus that you haven't seen in the past is called piecewise. Piecewise is where you have multiple pieces of graph. It's kind of like earlier when we had the word or. The reason you have ors in that is sometimes you have more than one pieces of graph. It's kind of like the first piece or the second piece. This particular problem has 3 pieces. I've drawn these dotted lines that separate it. It has 3 pieces of graph. So how's the problem work? Let me show you. It says realtors in a metropolitan area, let's just say DFW, study the average home price per square foot as a function of total square footage. Their evaluation yielded the following piecewise defined function. Piecewise just means the graph will look in pieces. It will not look like one nice little graph that's consistent. It'll have different pieces. It says find the average price per square foot of a home with a square footage of 1,400 feet. If you're dealing with piecewise, the first thing you got to do is figure out if I've got a function value, which piece do I use? So this problem has 3 pieces, 1, 2, 3. We have 1,400 square feet. You need to find out, is that 1,400 part of the domain of piece 1, piece 2, or piece 3? So question, I'm going to give you all 3 options first. Is 1,400 option 1 in between 1,000 and 2,600? Is it option 2 between 2,600 and 4,000? Or is it option 3 greater than 4,000? Where is 1,400 located? Between 1,000 and 2,600? 2,600 and 4,000? Or is it bigger than 4,000? The first one. 1,400 is in the first one, which means to get my solution, what I would do is I would say the price per 1,400 square foot, the average price, that's what the P stood for, would be the top equation. And where A is now 1,400. So 1,400 minus 1,000 divided by 40 plus 75. And I know I don't want to run us out of time, so I'm going to just talk quickly through the math. 1,400 minus 1,000 is 400. 400 divided by 40. Does anybody know what that number is? 400 divided by 40 is 10. So now we have 10 plus 75. What's 10 plus 75? So the average price for 1,400 square foot would be 85. So $85 per square foot. Kyrie, you still with me?
I'm on the phone.
Okay. That would be my average price per square foot. That's piecewise. So piecewise, all you have to do is first determine which piece of the equation do I use, and then you can get your solution. So this was the first equation because 1,400 was in between 1,000 and 2,600. Now part B gives us the same problem, but this time they changed the square footage. So part B, I'm not going to read the whole problem. All I'm going to do though is draw your attention to, it says 3,200 square feet. 3,200 square feet. I want you to think, is that option 1, 2, or 3? I'm going to do a countdown. So is 3,200 in between 1,000 and 2,600? Is it between 2,600 and 4,000? Or is it greater than 4,000? The number is 3,200. All right. 3, 2, 1. Your second and third. It's the second. 2,600 is in the second value. That means you would use the second equation. So P of 3,200 is equal to negative 3,200 minus 2,600 over 100 plus 110. For the sake of time, I want to do this math really quickly. 3,200 minus 2,600 is 600. Make it negative. It's now negative 600. Divided by positive 100 is a negative 6. So I have -6 plus 110. -6 plus 110 is 104. The average price for a house that's 3,200 square feet would be $104 per square foot. That would be the price. Your last DOL. I want you to get your answer for example 6 now. All right, now let's take a look at how this might look on the ACP. One thing I'm going to do though is I've added the circle, and truthfully, I don't want that here for this particular problem. We want to find the domain and range of this graph shown. So the domain, remember, that would be looking at the x values. And as I look across, I see that there is a break. There's 3 pieces here, which means there are 2 breaks. There's a break occurring in between these 2 pieces, which appears to me to be at +2. So let me insert that in. And there's another break occurring at 5. So at 2 and 5, you have a break in the domain. Since I'm looking at my options here, the problem with B is that it says there's a break between 2 and 5, sure, but there does not have anything in between the numbers 2 and 5, which means they ignore this entire piece of the graph. So B is out for that reason. And as I'm looking, D is saying there's no breaks whatsoever. Well, there is a break, so D is out. There's 2 breaks. So I'm specifically looking at breaks between 2 and 5, which this is saying that there's a break between 2 and that the graph is equal to 2, and that is equal to 5, which is not the case. So for that reason, C should also be out. A would be your correct answer. Now on the range, I want you to look at this. The range as you go left, or you go from the bottom to the top, there's only 1 break in between. You have this piece going from the bottom towards the top, and you have a break, and then both these 2 pieces overlap. That one break occurs at the y value of 0. So as you go left, if you go from the bottom of the screen towards the top, the only break in between is right there. It's at 0, and that's why this range breaks at 0. And the second term here, it says, what is the domain of this function? Well, going off our rules that we've learned today, there are 2 types. There will be a third, but for right now, we know that the first rule is that you cannot divide by 0. And the second rule is that a square root must be greater than or equal to 0. So when I look at the function f of x, there is division. So we cannot divide by 0. I'm going to take my denominator and say this denominator, when I replace this x, this denominator cannot equal 0. So x squared plus 3x cannot equal 0. That's going to be my domain. So let's solve this. I see I have an x squared. So I'm going to do a little factoring that we talked about in lesson 1-0. And in particular, I'm going to first check for a GCF. There is a GCF. In this binomial, both terms share an x. So I'll factor out x, which leaves me with x plus 3 does not equal 0. And according to the 0 product property that we learn in Algebra 2, the 0 product property states that if you're multiplying and you're ending up with a product of 0, or in this case does not equal 0, doesn't matter what inequality or equality symbol you have, as long as the product itself is 0, what you can do is set each one individually. So I could say that x itself does not equal 0 and x plus 3 does not equal 0. I could take each factor and set them as not being equal to 0. So this one's already solved, x cannot equal 0. And then here, if I just subtract the 3, I isolate the x, and we determine that x cannot equal -3 either. So there's 2 values x cannot equal. It's all reals other than these 2 values. So I'd be looking for the one that's all reals except for these 2 breaks. F doesn't have the break of 0, so it's out. Neither does G. H and J both have the breaks at -3 and 0. Remember, a union will represent a break, so that it has both of those breaks. H's have brackets. We're not supposed to have brackets. We're not equal to. So I would eliminate those brackets. The answer is going to be J.